I'll just briefly welcome you all to this second season of the N-Optimal seminar series. I'd like to acknowledge my co-organizers, Stefanos and Vladimir, for all their work on establishing this series. It's really thanks to their work that we have 8 excellent speakers lined up for this time around. And we're excited to get started again on our seminar series here. With that, I'll give the word to Stefanos, who will introduce today's speaker.
Yeah, thanks, Odin. Just before introducing Emiliano, just to mention, in terms of format and logistics, we're just going to follow the same format as in the previous series. So we'll have 45 minutes presentation, and then we'll can have a Q&A session for about 15 minutes. Feel free to use the chat. I mean, we'll keep an eye if you pose any questions there, or you can unmute yourself either during the presentation or at the end during the Q&A and pose your question to our speaker. So our first speaker for this second series of the N-Optimal seminar is Emiliano Dall'Anese. Emiliano received his PhD from University of Padova. And he's now an assistant professor in the Department of Electrical, Computer and Energy Engineering at the University of Colorado Boulder. So, Emiliano, thank you very much again for accepting our invitation. And the floor is yours. We're looking forward to your presentation.
Thank you so much, Stefanos, for the kind introduction. I'm going to start sharing my screen now. There we go. Can you see my screen?
Yes, yes.
Excellent. Again, thank you for the introduction, and thank you so much for inviting me to this seminar series. Today I will be talking about our recent works on database online optimization on network systems with specific emphasis on applications in power grids, given the main themes of this seminar series. Let me first thank some members of my group that put sweat and work in this research effort, starting with my postdoc Gianluca and my students Liam and Kilian, including Nicola, who was a visiting PhD student at CU Boulder from the University of Padova. And finally, let me also thank the funding agencies that are kindly supporting this line of research. So let me first give you a little bit of the 10,000-foot view of our research activities. And let us consider a given physical network system that is modeled by a given set of differential equations, where x is the vector of states, u is the vector of controllable inputs, and w is a vector of exogenous unknown inputs or disturbances. And of course, we also have the measurement equation. This is a very generic model that pertains to power grids, the main theme of today's talk, but is also applicable to transportation systems, if you embrace the well-known set transmission model, and also at the intersection of the two fields, electrified transportation. But more generally, we can also apply our methodologies to autonomous systems, autonomous vehicles in this particular case, or more recently, given the upsurge of COVID, to study the control of epidemics. So when it comes to optimizing a dynamical system of this particular form, we typically would like to formulate a given optimization problem to optimize the steady state operation of our system. And to do so, we may take as an input a given cost, constraints, as well as values of our disturbances or unknown exogenous inputs. And the cost can be built based on user preferences or models that are learned offline. And of course, we also need to utilize an algebraic representation of our system steady state, where here calligraphic M is our steady state transfer function that maps inputs into outputs steady state. Now, solving this optimization problem tantamounts to utilizing an iterative algorithm, which here is denoted with the generic map calligraphic T, and we repeat these algorithmic steps until convergence. And upon convergence, we can send down our optimal, in a well-defined sense, inputs U star to our dynamical system. So in this particular modus operandi, we can recognize that there are two inherent time scales. First off, we are assuming that our plant or dynamical system is infinitely fast, so that we can utilize our algebraic representation of the map, of the system. But furthermore, there is also an implicit assumption that during the execution of our optimization algorithm, and during the collection of our inputs, the cost, constraints, and inputs are static, and they are known. So what we like to look at is a scenario where we try to compress these time scales. And for instance, we consider the case where our cost, constraints, and inputs may change during the execution of our batch optimization method. Further than that, we would like to consider also the case where the vector W and the cost may be unknown. This is the case, as I will explain, where the cost models preferences of the end users, which may be unknown. In this particular case, I'm going to be presenting online optimization algorithms that are effectively implemented in closed loop with our plant, in the sense that we're going to be accommodating in our algorithmic steps measurements of the plant output. And I will establish relevant results in terms of convergence and stability of the resultant closed loop scheme. Just to give you a complete overview, we're also looking at the case where the dynamics of the plant and the dynamics of our algorithm have comparable time constants. And in this particular case, we can no longer assume, therefore, this time scale separation between plant dynamics and algorithms and the dynamics of the algorithm. In this particular case, my group has looked at the synthesis of online algorithms that effectively act as output feedback controllers and try to consistently drive the output of our plant for the dynamical system towards optimal solution of a time-varying automation problem. And the results that we were able to show pertains to practical stability and input-to-state stability of the resultant closed-loop scheme. This is not part of this particular talk, but I will be more than happy to chat offline about this additional line of work. All right. With this overview in place, let us dive into the concept of feedback optimization, and let us consider again a given network system with a generic algebraic map that maps inputs into outputs. And we associate with this network system a given time-varying automation problem. Here, T is the time index, or a given discretization of the temporal axis, where delta is a given sampling interval. And we can consider a time-varying cost function associated with both the inputs of the system as well as the outputs of the system. And we can also consider constraints, for example, associated with the output of the system. You can think of, for example, a quadratic cost moving over time to capture time-varying performance objectives. And in terms of constraints, both implicit on the inputs and on the outputs, you can consider feasible sets that are varying over time. Now, inherently, this time-varying formulation specifies optimal solution trajectories, UT star, associated with our inputs, as well as on the outputs based on this algebraic map. Now, if we were to utilize classical batch algorithms, where cost is known, the inputs are known, and I have sufficient time to run an algorithm to convergence, again, at every point in time, I need to run a sufficient amount of iterations to reach convergence. And then I move ahead, I receive a new cost, a new inputs, and I repeat again the process. We would like to move away from this particular setup, since this setup requires knowledge of the cost and constraints, and we would like to design online algorithms where at every point in time, I can afford performing only one algorithmic step. In fact, here you see that in this very generic algorithmic step, I have a temporal index and I no longer have an iteration index. And in designing this particular online algorithm, I would like to make sure that I'm able to track within a given error bound this optimal solution trajectory UT star that is formalized by this optimization problem. In doing so, I would like not to require knowledge of the disturbances or unknown exogenous inputs. And I also would like to handle the case where I may not know exactly the cost. Again, why am I doing that? Because, for example, I don't know what are the user preferences, and I would like to come up with a online algorithm with concurrent learning of the user preferences. Or I may want to learn physical models, namely the map, or pertinent barrier functions whenever I would like to relax my constraints. Now, just to set the stage, in the context of power systems, I can give a few examples. And the first one that comes to mind is a demand response setup, where I have a neighborhood with a number of distributed energy resources, and collectively, this neighborhood, where each house is connected to a single point of common coupling, excuse me, would like to operate in a virtual power plant fashion, providing demand response services. In this particular case, I can decouple the function j as a sum of functions, each one associated with a different DR, an HVAC system, an electric vehicles, and so on and so forth. And this particular JMT function models user preferences. What is the challenge? Well, the function may be unknown. For example, each one of you has a different perception of comfort, right? So utilizing synthetic models may lead to inaccurate problem formulations. Or, for example, each one of us has different preferences in terms of when an electric vehicle should be charged. In terms of output of the system, our Y, in this particular case, if we neglect electric losses in the circuit, can simply be given by the sum of the active power of the controllable DRs and the sum of the powers of uncontrollable devices. So this vector W is a vector that collects all the net powers consumed by uncontrollable devices. And as an example, my function CT of Y can simply minimize the deviation from a given reference input that is given to me as a DR or AGC signal. Or I can have a constraint in this form if I want to track this signal within a given error. As an additional example, I can consider real-time power flow, where in this case I look at the feeder as a whole. And I would like to provide services at the substation, namely control the power substation, while ensuring that all the electrical quantities are within limits inside the feeder. And in this particular case, there is a one-to-one mapping. Each, the vector UI can collect the power commands from the controllable DRs. And W is again the powers of all the non-controllable assets. In this case, Y is a vector that can collect voltage magnitudes at points that I would like to monitor, as well as the power flow at the substation. In this particular case, constraints can ensure again that the voltages are within given limits, or if I'm looking at the substation, I would like to manipulate the net power exchange in the substation to follow a given set point to provide, for example, flexible ramping products or AGC services. Very briefly, there is also a third application. I borrowed this image from NREL, where NREL is putting forth this concept of autonomous energy grids. And in this particular case, if I focus on something that NREL calls a cell, I can still formulate a given time variant information problem, where, for example, my CT or my constraint can capture, can be such that I can track reference points for the power exchange with each other cell. And again, my cost function can capture user preferences or comfort objectives. All right, with these examples in place, let me dive a little bit into the mathematics for the design of these algorithms. And just for simplicity, let me just focus on maps of this particular form, although everything that I explained can naturally be extended to nonlinear maps. And further than that, let me just focus on this particular problem for simplicity, although later on I will show you how to extend our findings to to problems with constraints also on the output. Let me add a number of assumptions first. First off, we're assuming that our function jt and ct are closed, proper, and convex. And further than that, the function is also smooth for every time instant t. And we're also going to be assuming that our set collecting hardware constraints or constrained inputs more generally is convex and compact for every t. Now, since this problem here is parameterized by quantities such that Wt that are time varying and also includes sets that are time varying, it is pertinent to capture the time variability of the solution set of this particular problem. And in particular, I can define this quantity here, sigma t, whenever the cost is also strongly convex, that capture the deviation in the optimal solution over two consecutive time instants. Whenever I have a compact set of optimizers, as opposed to a unique optimizer, I can readily leverage the concept of Hausdorff distance between two consecutive sets of optimizers. So this is going to be our metric to capture the time variability of our solution trajectory. Now, what we are after, again, is the design of algorithms that I denote with, the map calligraphy T, where the map is designed based on the cost and the set. And for this particular talk, I will be focusing on maps that are built based on first-order information on the cost. And I would like to point out that going from offline to online optimization is not an easy task. And even if I focus on the very basic strongly convex case, here in this figure on the bottom left, I'm showing the suboptimality of the objective function for a number of celebrated first-order methods as a function of the iteration index, which in this case considers the time index. And these convergence rates are very well known in the literature. However, now, when I switch from batch, namely when the cost is constant, to an online method, you see that the convergence behavior of these algorithms completely change. For example, the conjugate method, which is the best performing in this particular example in a batch setting, becomes the worst performing in an online setting. The heavy-ball method may actually diverge. And on the other hand, a very simple gradient descent method, which is the worst performing in terms of convergence rate in a batch setting, may actually yield the best performance in terms of in an online setting. With this in mind, in this particular talk, I will also try to touch upon a rigorous convergence analysis of online methods in order to characterize the convergence rate and the asymptotic behavior of online algorithms. Now, let's go back to our problem, and to set up the stage, let me write down the algorithmic step of the online projected gradient method, where again, we take the gradient of our cost function jt, as well as the gradient of our function ct associated with the output. And in this particular case, you see that in order for me to compute the gradient, I need to know the map of my network, and I also need to know the vector w, which in this case is the vector of unknown exogenous inputs. So running this online algorithm is clearly infeasible in some applications, such as power systems. If we think of Cambridge, Massachusetts, operating as a virtual power plant, you see that the vector Wt may be 46,000 dimensional. Why? Because you have approximately 46,000 households, and Wt, each entry Wt may collect the net power consumed by each household in Cambridge, Massachusetts. So in order for you to run one algorithmic step, you need to collect 46,000 measurements, something that is clearly feasible within, a time scale of seconds or milliseconds. Now, the idea, therefore, is to simply replace the algebraic map with current measurements of our system output. And in a particular case, we came up with this closed loop system where at every algorithmic step, we send down to our system our updated input, and then we measure the output of our network. Now, we also want to consider the case where we may not know very well the function jt, and therefore we need to rely on an approximate version of the function jt. As an example, I can also think of the case where I don't know very well the g, and therefore I can also use an approximate gradient of the second function. But let's focus on the first one. And in this particular case, there are several ways to obtain an estimate of the gradient of j. First off, zero-order methods. Unfortunately, zero-order methods are not applicable to our case, because we need to rely on function evaluations, various function evaluations at every step of the algorithm. What we did was to leverage Gaussian processes in order to estimate the function j from a parsimonious set of measurements. And before proceeding, I also want to acknowledge additional works that have looked at other shape-constrained regression problems. For example, when you want to come up with other ways to estimate the cost function based on some prior knowledge of the shape of the function. But let me take a little bit of the detour and to further dig into this GP-based optimization. And in this particular case, we are adding an additional feedback loop with effectively the human in the loop. And we are assuming that once every so often, this user can give us noisy function evaluations, namely can tell us their level of comfort or the level of discomfort, if you wish, with the use of particular devices, distributed energy source in this particular case. To further dig into this particular example, let me overview very briefly how a GP-based optimization framework may work. In this particular case, given a set of function evaluations that I collect in the vector zt, and this function evaluation corresponds to some given inputs ut, the posterior distribution of my unknown function jt, conditional on these data points, is a Gaussian process with the following mean and variance, where in order to compute the mean and the variance, I need to use a specific kernel. And based on this kernel, I can compute the kernel matrix associated with my data points, as well as the cross covariance between the data points and the point u prime, where I'm trying to extrapolate the value of the function. And once I obtain this particular posterior mean and variance, I can utilize various surrogate functions for our algorithm. For example, I can approximate the function j hat with simply the posterior mean, or to promote a trade-off between exploration and exploitation, I can augment the posterior mean with a scaled version of my posterior variance, to explore areas in my domain where the function is the least known. Just to show an example here, I'm assuming that the ground truth for my scalar value function is a simple quadratic color-coded in green. And here I'm showing the evolution of the posterior mean color-coded in blue, as well as the posterior variance, confidence interval, I should say, in light blue, with the increasing number of function evaluations. Here we just have 2 function evaluations all the way down to 18. So you see that, with the increasing of the number of function evaluations, I can approximate better and better the shape of my cost function, especially around this bottom, which is going to be quite important for the performance of our overall algorithm. This was just an example as to how to estimate our function j, but let's just go back to this feedback loop where, again, I have the plant in the loop as well as the end user to learn the cost function. And I would like to carry out a given performance. I would like to analyze the performance of this closed loop system under, again, possibly measurement noise and inaccurate estimates of my cost. To simplify a little bit the presentation, let me denote with capital FT our composite cost function. And let me also denote the algorithmic map with the symbol calligraphic T at time t, which is nothing but the composition between the projection and this classical gradient descent map. I'm also going to define with the var epsilon t the error that I commit in the gradient of the function j. And I'm also denote with c of t the error that I commit in the gradient of the second function, c of t, because of measurement errors. And I'm going to make the following standing assumption. I'm going to assume that each entry on the vector var epsilon t is a random variable that belongs to the class of sub-Weibull random variables. This class of sub-Weibull random variables is as follows. For a given parameter, theta var epsilon, a new var epsilon, I have that the following inequality holds for the probability of the absolute value of var epsilon it to be greater than or equal to a given kappa. So as you can see, this one specifies a given upper bound. And in fact, the sub-Weibull random variables captures a number of random variables that exhibits a given behavior in terms of the decay of the tails. For instance, the parameter theta captures the rate of decay of the tails, and the parameter nu is a proxy for the variance of my random variable. And I will provide examples shortly. What I want to mention first is that I'm going to assume that also each entry of my vector C follows a given sub-Weibull distribution. Why are we assuming these sub-Weibull distributions? First of all, because they're very handy when it comes to mathematical manipulations, since they are the class of sub-Weibull is closed with respect to some products and also product with scalars. But sub-Weibull distribution subsumes sub-Gaussian, sub-exponential, and any random variable with finite support. So it provides a very general framework for the analysis of algorithms with stochastic errors. Going back to our example on GP regression, we can also say that if we utilize a GP regression to estimate the function j, this assumption here is satisfied. In fact, if we use that one, the gradient, the posterior distribution of the gradient of j is a Gaussian process, which is therefore sub-Gaussian, which is therefore sub-Weibull. We're also going to be utilizing the following fact that we proved recently, that if we baptize as E, the sum of these two random variables, then the norm of E, again, E is the overall error that I commit in the gradient computation, is also a sub-Weibull random variable with a given parameter that from now on I will call theta, and a given proxy variance, which is related to the proxy variances of each individual random variable in these vectors. And from now on, I will call nu t the proxy variance of my overall norm error. All right. I will also going to make an additional assumption, regularity assumption, and I will say that although I have errors in the gradient, they are not too big, in the sense that I impose a given number of regularity assumptions on the expected value of the error and the variance. And these regularity assumptions simply say that on average, I still have a descent direction, or a direction with sufficient descent. So I want to rule out the case where I'm consistently going on the opposite side, and therefore have a diverging algorithm on average. With these particular assumptions in place, let me first consider the first case where our algorithmic map is contractive. This basically amounts to the case where our cost function is strongly convex, uniform in time, and I pick my step size alpha in an appropriate manner. In this particular case, we have that if UT is a sequence generated by our online algorithm with the plant in the loop and the user in the loop, the following happens. The expected value of the error between the point generated by my algorithm and the optimal solution at time t+1 can be bounded in the following manner, where the coefficient psi theta t is nothing but the product of the contraction coefficients over time, and the coefficient beta I can be related to the rho's in a similar fashion. The bottom line here is that the first term on the right-hand side vanishes over time because actually vanishes geometrically in t. And the second part here will capture an asymptotic error algorithm, and I will further elaborate on this point in a couple of slides. But before doing that, let me also state the second result, which asserts that with probability 1 minus delta, with delta in the interval 0, 1, of course, the error can be bounded by this particular, in this particular form here, where the right-hand side is of course a function of my delta, but is also a function of the proxy variance of my sub-Weibull random variable, as well as the temporal variability of my automation problem. So overall, these two bounds will explain in a probabilistic way the behavior at every iteration t of our algorithm. I would like to provide a couple of remarks on the high probability bounds, since this is one of the main novelties. And first of all, I would like to say that if we have a convergence in mean result, as I showed in the previous slide, we can readily obtain a result in terms of convergence probability by simply utilizing the Markov inequality. However, if you utilize the Markov inequality, you're going to end up with a bound that depends on 1 over delta, which will become rapidly vacuous as delta approaches 0. Whereas here, we have a dependence in terms of log 1 over delta. So it scales more favorably as delta tends to 0. Furthermore, as a simple corollary, we can also show that asymptotically, our error, tracking error, is bounded. So this is a result in terms of ultimate boundedness in probability, almost surely, where rho is an upper bound on our contraction coefficient and delta is an upper bound on our temporal variability sigma t. And of course, epsilon t is a bound on the expected value of the norm of the error. If we consider vanishing errors and also vanishing temporal variability, we can recover well-known convergence results in terms of almost sure convergence of Combet and Pesquet. And as a final remark, I also want to mention that we can also provide similar bounds for functions that are not necessarily convex, but satisfy the PL condition. Before moving on, I also want to make a connection to well-known results in terms of input to state stability for discrete time systems, dynamical systems, and because in fact we can view our algorithm as a stochastic discrete time dynamical system. And based on this particular bound here, I can work out the math, and by again adopting some definitions, such as rho being the supremum of my contraction coefficients over time, I can come up with this particular bound. This particular bound here on the error in expectation is very interesting, because if you look at the right-hand side, you can rapidly recognize that this first function is what we call KL function. Whereas the second two terms are nothing but K infinity functions in the supremum of the norm of the error in the expectation and the supremum on the temporal variability. So this is a classical input to state stability in expectation for our discrete time stochastic system, whereby the the input to the stability result is with respect to the error that we commit in the gradient computation, as well as the variation of our solution over time. To mirror some well-known results of Sontag and Qualforce, we can look at this as a counterpart of the ISS result in UT star dot whenever we consider continuous time dynamical systems. All right, now, so far I've looked into the contractive case, namely when the function was strongly convex. I also want to briefly mention that when the function is convex but not strongly convex, we can still have meaningful analysis. And in this particular case, the analysis that we can have is in terms of the cumulative fixed point residual. You can think of the cumulative fixed point residual as a proxy for the convergence of the algorithm. And also with due implications on the convergence in a weak sense of the sequence of our UTs. I'm not gonna spend too much time on this bound. I also want to mention that both the bounding expectation and high probability have a similar mathematical form with a given term that eventually will vanish. Consider also 1/t on both sides, and something that will dictate my asymptotic error in the cumulative fixed point residual. All right. So now that we look at this particular setup, let me also tackle an additional challenge. Here we're assuming that we have at our disposal readings, measurements of our network output time step. However, what if we may not receive measurements at every time step? This is because of packet losses, faulty measurements, and applications that may arise, especially in a power system setting. In this particular case, we can rewrite our algorithmic step in this particular form. We compute an algorithmic step as before, only vector measurements is received. However, if the vector of measurement is not received, the best I can do is to stick with my current decision. However, I need to project it into the new feasible set. For example, if the power available from PV system is diminishing, well, my power set points for a PV system needs to be brought back into the feasible range at the current time t. Now, mathematically, I can rewrite this particular switching algorithm in this particular form by using a random variable that takes values in 0, 1. More specifically, when the measurement is received, and therefore I perform an algorithmic step, and it takes the value 0 when the measurement is not received, and therefore I perform a very simple projection step. So we're going to be assuming that Vt is a Bernoulli random variable with a given parameter p, which is uniform in time for simplicity of exposition, and the variables Vt's are IID over time, and they are also independent of the random variable that model errors in the gradient errors. With this particular assumption in place, there is a particular intermediate step where if we look at this particular, again, stochastic algorithmic step, we first need to characterize the following quantities. If we denote as capital delta t, the sum of our random variables, more specifically a sum of t consecutive random variables, then we have that rho to the delta t with this zero constant, summation of rho with rho constant times this elevated to this random variable times the random variable that models our errors whenever the algorithmic step is performed is a sub-Weibull random variables. Now you start seeing why a sub-Weibull model comes very handy. And in particular, we can also compute the rate of decaying of the tails of this particular random variable, as well as the proxy variance. The proxy variance is once more related to the proxy variances of each individual error in the gradient, as well as this function eta t, which we proved is a function that is monotonically decreasing with respect to time. With this particular intermediate step, we can have the following result, very similar to the one I showed before. But in this particular case, we have that this switching algorithm produces a sequence UT that still follows within a bound and error our optimal solution trajectory, X star T. The only difference, unfortunately, is in this case, we have a P on the right-hand side that accounts for, again, the randomness in receiving measurements YT. And the other coefficients, for example, the beta, the omega, and the chi, are dependent upon a different contraction coefficient, which in this case is given by the following form, where P multiplies the contraction coefficient of the nominal algorithm that I would have had should I receive the measurements at every time step T. This is again a resulting mean. We can also provide the resulting high probability. And in fact, for every given delta 0, 1, the error is bounded with probability 1 minus delta by this particular bound here, where again, it is very similar to the one that I showed before in a mathematical form. The difference is the presence of this parameter P, which was the parameter of the Bernoulli, and now the decaying rate is dictated by this function eta t instead of having a geometric decay of this first term. So this complete the characterization of the algorithms that we proposed with the plant in the loop and the user in the loop to learn the function. Before showing you a couple of numerical results, I just want to point out that we can readily apply everything that I showed you to these more general problem setups whenever we consider an online primal-dual method as opposed to a projective gradient method that I showed you so far. The analysis is carried out so long as you synthesize the online primal-dual method based on a regularized version of the Lagrangian. Namely, when you take the Lagrangian associated with this particular constraint problem and you add a quadratic term with respect to the dual variables in order to make the regular Lagrangian strongly convex and strongly concave. With this in mind, I'm going to move to a couple of numerical results. Let us consider, for example, the case where we have a collection of distributed energy sources in the distribution figure. And this distribution figure is actually connected to 2 points of common coupling. Let us consider a simple linear model that you can derive from a linearization of the power flow equations, or in a demand response setting, whenever the losses can be disregarded. And in terms of cost function, CT associated with the output, where the output here is nothing but the 2 powers, the 2 points of common coupling, let us consider the deviation from two given reference points for these 2 points of common coupling. And let us estimate the cost function associated with each of the users owning the DRs using Gaussian processes, using, for example, 5 initial samples and then collecting additional samples at different rates. And I will elaborate further on this. Let us suppose, for instance, that the Y ref decays linearly for both points of common coupling, although I can also look at more exotic trajectories. And the sum of all the non-controllable assets, powers of non-controllable assets, behaves in the following manner for the 2 points of common coupling. So let's look at the results in terms of tracking error of our algorithm. And let us consider the clairvoyant case where our online method knows the function and has access to measurement every time step. So this is the blue trajectory and represents a little bit the benchmark for our algorithm. Let us consider now the online projected gradient method when you utilize the GTs. And we consider different probabilities of receiving a measurement from the network. In the worst case here, is basically flipping a coin, and we receive a measurement by simply flipping a coin. So you see that the tracking error clearly deteriorates with the decreasing of the P, the parameter of our Bernoulli, but still the behavior that you obtain is verified by the theoretical bound that we found. And again, this temporal variability that you see here is due to the, if I go back, the temporal variability of our non-controllable loads, which again, we don't measure. We just rely on measurements of the power at the point of common coupling. I also want to show an example how the tracking error normalized in this particular case behaves when we have different noise levels in the function evaluation. So, for example, the case where the user is a bit uncertain about his, her, or their preferences, and therefore the function evaluation is more noisy. In this particular case, we consider the case where the user sends back a feedback every 12 minutes. And we see the evolution of the relative tracking error over time for different noise levels. I mean, as expected, you see that we achieve a lower tracking error whenever the noise level is lower, right? This is very expected. Something a bit more interesting is to assess the normalized tracking error over time whenever we receive, I mean, based on how frequently we receive the feedback from the user, or namely how frequently we receive the function evaluations, and in par with the same noise level. So here we consider the case where we receive it every 5 minutes all the way up to 30 minutes. And here you can see that there is a nice trend. Of course, our tracking error improves with the increasing of the frequency of function evaluations. However, if I'm looking at a particular asymptotic, behavior for sufficiently large times, the error is not so different when I go from 5 to 30 minutes. And this is an indication of the robustness also to our closed loop method with respect to errors in the gradient. I would like to conclude the talk by mentioning that these particular algorithms can also go from a synthetic implementation all the way down to the field. And in fact, as part of an effort that was with NREL, my colleagues at NREL, that was funded by ARPA nodes, we implemented a subset of these methods in a microgrid in Sonoma Valley, where we had a number of controllable assets that include PV systems, energy storage systems, hydrogen electrolyzers, gas turbines, and the low controllable loads were simply water pumps. And we ran these algorithms for more than 24 hours straight. Just to give you an idea, this is the net power at the point of common coupling that the microgrid has over the course of one day when no controls are implemented. In this particular figure here, we were trying to have the net power at the point of common coupling following a given reference signal, which is color-coded in black. And you see that we tested a variety of control signals, going from step changes with different frequencies, and we also implemented ramps as well as other types of signals. And you can see that this algorithm allows the microgrid to effectively track within a given error these reference signals that are set forth at the point of common coupling. We also implemented a feedback loop where we consider also voltage limits. And here we run a different experiment where on top of tracking a given reference signal for a point of common coupling, we also made sure that the voltage limits were satisfied. And for a first period, the voltage limits were plus minus 1%. And then we loosen up a little bit to plus minus 2%. And you can see that also the voltages are regulated most of the time within these bounds. This flickering is mostly due to water pumps shutting off and on, thus creating this flickering. This concludes my talk. I wanted to look at time-varying optimization methods to model optimal trajectories of network systems. And I wanted to show the design of online methods with feedback to track these optimal solutions. I believe that our results extends the theory of first-order methods whenever you consider the plant in the loop and also the user in the loop. And I wanted to provide bounds both in expectation and in high probability under the sub-Weibull model for the error. I try to cover application power systems, although our group is also looking at additional applications in transportation systems and more recently in healthcare problems. Future steps will further look into these data-driven methods to further develop algorithms for other applications and derive other convergence bounds. Thank you so much for your invitation again and for your attention. I will be happy to respond to any question that you may have.
Thank you very much, Emiliano. It was a super interesting talk. Let's see if we have some questions from the audience. Yeah, there is one in the chat. Emiliano, yeah.
I can. So first, I wonder whether you propose online algorithm can provide any guarantee for a worst case regret. My other question is that if the objective function is not convex, but for example, it is some modular, can we still use these online algorithms? These are two very nice questions. Thank you for asking. So in the first case, providing a worst case regret, so we can tie certainly the tracking error and the fixed point residual to a concept of regret, especially in the first case. In the second case, it's a bit more delicate. But remember that unfortunately here we're looking at stochastic algorithms. So the best that we can do is to provide a statistical characterization of the error, as we did in this case. You can think of the high probability result as some sort of a worst case, if you wish, wherever you bound your error with sufficiently high probability. You cannot do a worst case analysis unless you prove that the probability density distribution of your error has a finite support. That in this case, you can just look at the support of your random variable. I hope this makes sense. The second question is extremely interesting because today I just dealt with convex functions or even strongly convex. When you have non-convex functions, but you assume that you have strongly regular points, the results that I show today may be translated to that case so long as you start the algorithm within the contraction region of your strongly regular point. And for example, we wrote a paper on that, but there are also other people, such as, Professor Vey, that has looked at this particular problem. The particular challenge here is that we have gradient errors. So you got to impose additional assumptions such that the error that you commit in your gradient does not make the algorithm jump over the contraction region of your strongly regular point. Long story short, you can, but there is much more work to do because of these particular technicalities.
Thank you, Emiliano. Any other questions? Again, yeah, there is one from Young.
Hi, Emiliano. So I have a question about the prompt setup. So in the beginning, you say you have dynamic system, and then you look at the steady state optimization. Excellent. And you assume Y will be a algebraic map from input and disturbance. Right. I'm wondering, like, say, if the system is maybe unstable. So if you have input, have a disturbance, and your Y, let's say, maybe unstable, how would you deal with this case? Or you assume the system is overall stable for any input disturbance, you will have a steady state.
So this is an excellent question. Thank you for asking. So it is true. Today I focus on cases where I basically model my system via an algebraic map. let me first mention that we do have works that consider the case where our online algorithm is in close loop with the dynamical systems. So we bypass this inherent timescale separation assumption. And if I go back to the slides a moment, we are precisely looking at, let me see. We are precisely looking at this particular case here, right? Where we have an interconnection between our online algorithm, in this case, implementing continuous time, and our continuous time dynamics of the plant. And I will be happy to chat more about this. But yes, an underlying assumption is that our system is already stable. And therefore I can write down in the case of today's talk, a legitimate steady state map. So there is an inherent assumption that I have a stabilizing loop in the dynamical system. Now, having said that, I will be happy to chat more offline, but we also have works where we show that we can also handle plants in these plants that are switching, and in particular, they switch between a stable mode and a number of unstable modes. In this particular case, we provided results in terms of stability and input to stability under given assumption on the how frequently you switch between stable and unstable modes. Does this answer your question?
Yeah. Thank you.
Thank you so much for asking. We'll be happy to chat more.
Yeah, I have another technical question. Like on page, I think page 18, you mentioned like you need to estimate the gradient of J and also another matrix G. And you mentioned like G is also unknown, but you didn't say how you handle that part. Yeah, the G matrix.
Yeah,
page 18, I think.
Okay, so we're going this way, right? So yeah, that's a very good question. Thank you so much. So yeah, as an example today, I focus on the case where I estimate J through functional evaluations in this particular setup via Gaussian process regression. You can do the same, for example, for the second part in two cases. So first, you can assume that if we stick to linear models, that G is unknown, and for example, there have been works that look at utilizing the fundamental lemma to estimate the matrices A, B, C, D for a linear dynamical system, and therefore the G, or works that have looked at a direct estimation of the matrix G. But my comment on the C was that, for example, you may not know what is the algorithmic map, for example, the transfer function between the U and the Y, and therefore you may want to use Gaussian process regression or other methods also to estimate this map. Once you estimate this map, you utilize the Jacobian, which at this point is an estimated version of the Jacobian. Does it make sense?
Yeah, thank you.
Yeah, thank you so much.
Okay, let's see if we have any last question, because it's almost 12 o'clock. And yeah, I think we're perfectly on time. Thank you very much again, Emiliano, and thank you all of you for joining the seminar today. I think we can conclude here. The next event of this seminar series would be on the 18th of October with Mariam Kamgarpur from EPFL. So we're all looking forward to see you there. Yeah, have a nice weekend. Thank you very much again for joining.
Thank you, everyone.